Projectiles, Lesson 3, Equation of the Trajectory. So we're going to go straight in with an example. Let's label this diagram with the information that we are given in the question. A particle is projected from point O with initial speed 40 meters per second. Let's draw that on, 40 meters per second, at an angle of 30 degrees above the horizontal. We've now got to find the Cartesian equation of the particle's trajectory. So remember, trajectory is another word for path. So in other words, we're finding a Cartesian equation for the path of the particle, which is this parabolic curve. So we want to find the Cartesian or x and y equation for this quadratic curve. So the first thing that we're going to do is pick a point on the curve. And I'm going to label that point P. And P is going to have coordinates x and y. So imagine the curve now on a set of axes. So what we want to know is what are the coordinates of P, and let's then find a relationship between x and y. So let's draw on the rest of the information. We need to make sure we've included our acceleration, which of course is downwards and equal to g. I'm going to resolve this initial velocity into its two components like that. So we have a horizontal component of 40 cos 30 and a vertical component of 40 sine 30. And what we're going to do is we're going to explore the motion between O and P, and we're going to split this into its horizontal and its vertical components. So let's look at the journey from O to P. So horizontally, we know that we have a constant speed, which is equal to 40 cos 30. We can use speed equals distance travelled divided by time taken to get there. And if we're looking at the journey from O to P, we know that the distance is the x-coordinate of P, which we've just called x. The time we'll call t, capital T, which is the time taken to get from O to P, and the speed is 40 cos 30, which of course we can then rearrange all this to give us x equals 40 cos 30 multiplied by t, which is 40 multiplied by root 3 over 2 t, which gives us x equals 20 root 3t. So we actually have an equation for the horizontal distance travelled for x in terms of t. Let's do the same with the vertical motion. I'm going to choose up as my positive direction. I'm going to identify my suvat information. Displacement is going to be y, the y coordinate of point P. U is equal to 40 sine 30, which works out to be 20 meters per second. V, we don't know, it's the velocity at P. A is equal to negative g, and t is the time taken to reach point P. So, as we have done fairly often in some of these questions, we can rule out v, and we need to use s equals ut plus a half at squared. So y equals 20t minus 4.9 t squared. And notice we have an equation for x in terms of time, the horizontal distance travelled, and an equation for y in terms of time, which is the vertical distance travelled. We actually have a pair of parametric equations. So this links in very nicely with the work that you will have covered on parametric equations. And in that work, you will have looked at identifying a Cartesian equation from a pair of parametric equations by eliminating a parameter. And that's exactly what we're going to do here. We are going to eliminate the parameter t, which represents time. So if I call this equation 1 over here and equation 2, I'm going to take equation 1 and I'm going to rearrange it as the simpler of the two to work out what t is. So t is equal to x over 20 root 3. And we're going to substitute this into equation 2, which gives me y equals 20 multiplied by x over 20 root 3. So just make sure you can follow this carefully. I'm replacing t in this equation with t as it is in terms of x. So I've just done the first part, and we're just about to look at this second part here. So minus 4.9 multiplied by t squared, which is x over 20 root 3 all squared. This then simplifies neatly to give me y equals x over root 3 minus 4.9 x squared over 1,200. You can rationalise the denominator in the first part of this as well if you wish to. Now, this is the equation connecting x and y, where x is the horizontal distance travelled by a particle and y is the vertical distance travelled by a particle, but we can think of x and y as coordinates. So this is the equation connecting x and y, which means it's the equation of the trajectory of the particle. And it's Cartesian because it's in terms of x and y. These equations here also give us information about the trajectory, but they are parametric because x and y are both defined in terms of a third parameter t. So let's have a look at another example. We're going to read through this information, then annotate this information onto a clear diagram. We have a golf ball hit at an angle of 60 degrees to the horizontal from a point O on level horizontal ground. Its initial speed is 20 meters per second. The standard projectile model in which air resistance is neglected is used to describe the subsequent motion of the golf ball. At time t seconds, the horizontal and vertical components of the displacement from the origin are denoted by x and y. And we need to write down equations for x and y in terms of t for part 1. Part 2, we need to find the equation of the trajectory and show it's this. And then part 3 and part 4, we're then going to use the information that we have established. So first things first, we need to annotate a clear diagram with this information. So here we have our projectile path. I'm going to label up the axes again, as that's helpful in thinking about the Cartesian equation of the path and thinking about the trajectory as a graph. Now, we know that the golf ball was hit with a speed of 20 meters per second. So I'm going to mark that onto my diagram like this. And we know that the angle of projection is equal to 60 degrees. We can mark on the components of this velocity. Horizontal component 20 cos 60, vertical component 20 sine 60. And we'll mark on as well the acceleration due to gravity, which is equal to g and acts downwards. Now, we're going to pick a point on the path of the particle, and we'll give this coordinates x and y to represent the horizontal and vertical distances travelled. So we're going to analyse the motion from O across to P, and we're going to do this horizontally and we're going to do this vertically. Let's start with the horizontal direction first of all. We're going to make use of the fact that the speed is constant. Speed equals distance over time. Now the speed is 20 cos 60. The distance travelled is x to reach point P, and the time taken, we'll just call that t. So we can say x is equal to 20 cos 60 multiplied by t. Cos 60 equals a half, so x is equal to 10t. And we have one parametric equation. Now, let's have a look at the vertical motion. I'm going to choose up as positive, and let's identify some suvat information. From O to P, the displacement is y. U is equal to 20 sine 60. Sine 60 is root 3 over 2, so this comes to 10 root 3. V we don't know. A equals negative g, and the time is the time taken to reach P. So again, this is becoming very familiar. We want to use the suvat equation, S equals ut plus a half at squared. And substituting into this, we have y is equal to 10 root 3 multiplied by t minus 4.9 or minus a half g. We can write it as that, t squared. So we have an equation for x up here, and we have an equation for y over here, both in terms of the parameter t. I have noticed in the question they've used a lowercase t rather than an uppercase t, so we will just finish this off by writing out the answers to part 1 in terms of lowercase t. X equals 10t, y equals 10 root 3 t minus a half g t squared. Part 2 asks us to find the equation of the trajectory by eliminating the parameter t, so let's do that. So equation 1 clearly gives us t is equal to x over 10, and we're going to substitute this into the equation for y. So everywhere there is a t in the equation for y, we're going to replace that with x over 10. Let's do that. So y is equal to 10 root 3 multiplied by x over 10 minus 4.9 multiplied by x over 10 all squared, and this comes to x root 3 or root 3 multiplied by x minus 0.049 x squared, because 4.9 divided by 100 is 0.049, and that is what we were required to get to. Part 3, find the range of the ball. So in this quick sketch diagram, I've just illustrated what the range actually is again. It's this horizontal distance travelled. So at this point here, at the end of the particle's journey, we'll call this point B, we can see that the y-coordinate of the trajectory is equal to 0. So what I'm going to do is I'm going to take the equation for y and I'm going to replace y with 0. So root 3x minus 0.049 x squared equals 0. We can factorise out x, so root 3 minus 0.049 x in the bracket equals 0, and this then gives me x equals 0, which is when the particle is at the start of its motion and has a y-coordinate of 0, and then this part here gives me x is equal to root 3 over 0.049, which is when the particle is actually at B, and we can evaluate this. It comes to 35.347 or 35.3 metres to 3 SF. So this is the range of the projectile, so the distance OB. So the last part of the question, a bird is hovering at 2016. Find out whether the ball passes above the bird, below the bird, or hits the bird. So I'm interested in finding out what happens when x is equal to 20 for the particle. Remember, the particle is following this red path here. So if x equals 20, we can substitute that into the Cartesian equation. So y equals root 3 multiplied by 20, subtract 0.049 multiplied by 20 squared, and let's evaluate this. Now this comes to 15.0410, which is less than 16 metres. So when the x-coordinate of the particle is 20, its y-coordinate is about 15.0, which means the bird, which has an x-coordinate also of 20, so is vertically in line with the particle, has a y-coordinate of 16, which means that the bird is above the ball. So we can say, and it's important that we do actually answer the question, so the ball passes below the bird, and we can also supply a distance. So 16, subtract 15.041, etc., gives us 0.958 to two significant figures, 0.96 metres. So the ball passes below the bird by 0.96 metres. Let's have a look at a second example. Now there is a lot of information in this and a large number of parts to this question. We will need to draw quite a detailed diagram in a moment, so make sure that you can see the question as well as we sketch the diagram through. So a ball is kicked from horizontal ground. It leaves the ground at a speed of 25 meters per second and at an angle theta to the horizontal, and we're given some information about cos theta and sine theta. So let's work this through by starting to draw a diagram. So here we have our particle's trajectory sketched. I've added the initial velocity and its two components and the acceleration due to gravity. Now the first part of the question is simply finding the parametric equations that describe the particle's horizontal and vertical position at time t. So let's have a point P again with coordinates x, y, and the time is going to be t at this point. We're going to analyse the motion that takes us from O to P, looking at the horizontal motion and then the vertical motion. So horizontally, we know that we're going to use speed equals distance travelled over time taken. Now the speed is 25 cos theta, the distance travelled is x, and the time is t. So this gives us x equals 25 cos theta multiplied by t, but the question actually tells us the value of cos theta. It's equal to 0.96. So this then simplifies down to give us x equals 24t, which was as required. So there's the first of our parametric equations. Let's now look at the vertical motion. So I want to identify a positive direction, which will be upwards, and let's fill in our Suvat equation information. S equals y at the point P, u equals 25 sine theta, and we know that sine theta in the question is given to us, it's 0.28, so that allows us to work out that u is equal to 7 meters per second. V we don't know, A is negative g, and T is, we'll call it T. So ruling out V here, we're going to make use of S equals ut plus a half at squared again. So I'm going to substitute into this. I'll do this down here with a little bit of space. So y is equal to 7t minus 4.9, that's a half of g, t squared. And I have my second parametric equation of the pair. Now, part 2 asks me to calculate the maximum height reached by the ball. I can do this looking at this point here, which we'll call A, by applying a Suvat equation. I can also do this by using the y result here and differentiating it. There are many ways in which we could actually do this question, so this is not the only method available to us. So at the maximum height, I'm going to fill in the Suvat information that I know. S is what we're trying to find. U is equal to 7. We know that. That's 25 sine theta, which worked out to be 7. V, the velocity, the vertical velocity is 0 at the maximum height. A is negative g and t is t. So from here, I can rule out the time because that's not actually what I want to work out. And then I can use v squared equals u squared plus 2as to work out my value of s. Please be careful here. The s does look a little bit like a 5, but it is an s. So rearranging this equation gives me my maximum height, which is equal to 2.5 meters. So just to point out, if you wanted to, you could actually have differentiated the result for y. dy by dt is equal to 7 take away 9.8t. You could then set that equal to 0. So at the maximum height, we know that dy by dt is equal to 0, so that gives you 7 minus 9.8t equals 0. T then equals 7 over 9.8, and if you substitute this back into the equation for y here, you will find that you get 2.5 meters again. So that's an alternative method that we could have used. Part 3, calculate the times at which the ball is at half its maximum height. So half of the maximum height would give us a height of 1.25 metres. So remember the equation that we have for y equals 7t minus 4.9t squared. So 1.25 equals 7t minus 4.9t squared. And we can rearrange this and we see that this is a quadratic equation. So we can solve this on your graphical calculator or use the quadratic formula to solve it. It doesn't actually factorise, unfortunately, but the values of time that you will get are 1.2193 and 0.2092. So these are the two times. We'll just round these to 3 significant figures, but we will also make sure that these are either stored in calculator memories or we have sufficient accuracy written down to be able to use these values again. Now there's another part to this. We have to find the horizontal distance travelled between these times here, which is why we did need to preserve the full accuracy as well. So let's work out the two x values. If t is equal to 0.2092, the x distance can be calculated, remember, using our formula for x, which was x equals 24t. So x then equals 5.021 ... If t equals 1.219 seconds, etc., x then equals 29.264, etc. So the difference between these is equal to 24.243 ... or 24.2 metres to 3 significant figures. Now part 4 has 3 subparts to it. We'll do them separately. Part A. So determine when t equals 1.25 seconds the vertical component of the velocity. Now we can do this using a Suvat equation, or we can use the fact that we know that y is equal to 7t minus 4.9t squared, and we have previously differentiated y with respect to t, so we get 7 minus 9.8t, and this is of course the vertical velocity. So at t equals 1.25 seconds, we can evaluate this velocity by substituting in 1.25, which gives us an answer of negative 5.25 metres per second. The question actually asked for the vertical component of the velocity, so I'm going to leave it as its negative value. It's not asking for speed, it's asking for velocity. Now, part B, we have to determine whether the ball is rising or falling. So at this time of 1.25 seconds, we can see that the vertical component of the velocity is negative. We can see that there. Now, we defined up as positive, which means that if the velocity is negative, the ball must be falling downwards. So i.e. the vertical velocity acts downwards or is in a downwards direction, and the ball is falling, not rising. Part C of this part of the question asks us to find the speed of the ball. So we know that the velocity will have a horizontal component and a vertical component, and the vertical component is minus 5.25 or 5.25 downwards. To find the speed, we're going to need to find the hypotenuse of this right-angled triangle. Now, the horizontal component of the velocity is constant. It's the same as the initial horizontal component of the velocity, and we worked that out quite some time ago. It was actually equal to 24. If you remember, it was equal to 25 cos theta, and theta was equal to 0.96. So we simply have to apply Pythagoras' theorem to get the speed of the ball. So 24 squared plus 5.25 squared, and then square root this result. This comes to a value of 24.567 ... 24.6 metres per second to 3 significant figures. Part 5 asks us to find the equation of the trajectory. So we're going to take our equations, our parametric equations for x and y in terms of t, and as we've done previously, we will rearrange the first one so that we have t in terms of x, t equals x over 24, and we will substitute this into equation 2. So we have y equals 7, and in place of t, we will substitute in x over 24. So we have y equals 7 lots of x over 24 minus 4.9 multiplied by x over 24 squared. Now this is a show that question, so we have to show that our answer can be expressed in the same form as that given. So let's simplify this a little bit further. So this comes to 7x over 24, subtract, and if we simplify the numbers here, we end up with 49x squared over 5,760. So all we then have to do is factorise out 0.7 over 576x, and we are left with the 240, take away 7x, which is the answer given in the question. Now the last part of this asks us to find the horizontal range of the ball. We know that this is where y equals 0, again for the second time. So if we set y equal to 0, well, the equation is already factorised for us. And of course, there are two possible routes, x equals 0, which is the starting point, so it's not the point we're after. This x value over here will give us 240 over 7, and that is our horizontal range. So remember, this is where the projectile strikes the ground again and has a y-coordinate of 0. There are two places where the y-coordinate is equal to 0. One is at the origin, one is at the very end of the journey, and this horizontal distance travelled, or the x-coordinate at this point, which we've worked out to be 240 over 7, is equal to the range. And the last example, slightly different as it involves vectors. So a projectile P travels in a vertical plane over level ground. Its position vector r at time t seconds after projection is modelled by this result here. Distances are in metres and the origin is a point on the level ground. Part 1, write down the height from which P is projected. Now, this equation here takes the format r equals r0 plus ut plus a half at squared. It's a vector Suvat equation when the point of projection is not the origin. So the initial point of projection is not 0, 0. So at time t equals 0, the particle is at the point with position vector r0. So the point of projection is 0, 5. So the height from which P is projected must be 5 metres above the ground. Now the value of g in the model, well, we can see from here, this part here gives us our half a, and so the acceleration that they're using is a equals 0, 10, or 0, negative 10. So that means the value of g that they're using is 10 metres per second squared. It's a negative because we've defined I and j in these directions here, and of course the acceleration is downwards like that. So there we are. Part 2, find the displacement of P from t equals 3 to t equals 5. Okay, so what we're going to do is we're going to substitute in t equals 3, and we're going to find out what r is, and we're going to substitute in t equals 5 separately, and we're going to find out what r is as well. So when t equals 3, r is equal to 0, 5 plus 90, 120 minus 0, 5 multiplied by 9, and then this simplifies to the vector 90, 80. And we can do the same thing, substituting t equals 5 into the same result here, and we get r equals, and the vector is 150, 80. So we can see that they have the same y component but different x components. So if we imagine the journey of the particle at t equals 3, it's at a point with coordinates 90, 80, and at t equals 5, it's at a point with coordinates 150, 80. So the displacement between these 2 points is this vector here, and it's simply equal to 60, 0. Now, the last part of the question involves finding the equation of the trajectory. So, looking at the displacement vector, all of the information is put together here for us. Let's look at the I components to begin with. So, horizontally, like so. So, this then gives us x equals 0 plus 30t, and then minus 0t squared, so just x equals 30t. Now, if we look at the j components, instead, we get y equals 5 plus 40t minus 5t squared. So here are parametric equations. Now, we are asked to provide a Cartesian equation, so as we've been doing previously, we will start by rearranging the simpler equation for t in terms of x, t equals x over 30, and we will substitute this into the equation for y, so y equals, and then at every point where there's a t, we will replace that with t in terms of x instead. So 5 plus 40 multiplied by x over 30 minus 5 multiplied by x over 30 all squared. And then a little bit of algebraic simplification will show very quickly that this simplifies to the result expected. And we are finished. Now, the very last thing that we're going to do in this topic is to look at generalising what we have done so far. So look at the information we've got. A particle is projected from a point O with a speed u meters per second at an angle theta above the horizontal. The only force acting is the weight of the particle. So here is our setup. I'm going to add in the acceleration due to gravity, g, downwards like so, and I'm also going to fill in the 2 components, horizontal and vertical, so u cos theta horizontally and u sine theta vertically, of the initial velocity. Now, let's add in a little bit of further annotation to our diagram. So this point over here, which I'll label A, is the point at which the particle is at its maximum height. So I'm going to call that maximum height h. And of course we know at A, the vertical velocity is equal to 0 at that point there. Let's label another point here at the end of the motion, which is B, and then we know that this distance, which I'll highlight in yellow, this is the horizontal range of the particle, which I will call R. Now, we know that at point B, the time taken is the time to complete the whole journey, and that is referred to as the time of flight. So we're going to analyse the motion from O to A and then from O to B and see what information we can generalise. We will need all the information on this diagram, so make sure you've got a nice clear sketch of this ready as we proceed. So let's start off with looking at the journey from O through to A. So I'm going to start off by analysing the horizontal movement, first of all, and we've been using the fact that the speed is constant, which allows us to use speed equals distance travelled over time taken. Now, the horizontal speed is u cos theta, and that's the distance travelled divided by the time taken. So I'll just call this distance over time for the moment because we don't have any further information. But let's look at the vertical movement from O through to A. We'll choose up as our positive direction, and we'll fill in some SUVAT information. So from O up to A, we know the displacement is h, u we know is u sine theta, v equals 0 at the maximum height travelled, a is negative g, and t is the time. So the information that I am going to focus on, s, u, v and a, so I'm going to rule out t here, and this leads me into v squared equals u squared plus 2as. So 0 equals u sine theta all squared minus 2gh. And I'm going to rearrange this result so I get a result for h. So h is equal to u squared sine squared theta divided by 2g. And I have a general result for the maximum height. Remember, h is the maximum height achieved by the projectile. Let's now explore what happens on the journey between O and B. So the full journey. Let's start with the horizontal direction again. Speed equals distance over time. Remember, the speed is u cos theta throughout the horizontal motion. The distance travelled is the horizontal range r, and the time taken is t, which is the time of flight. Now, we need the vertical component of the motion in order to be able to deduce anything further. So let's fill in some SUVAT information. S, the displacement, is 0 when we're at point B. U is equal to u sine theta. V we don't know. A is negative g, and t is t, the time of flight. So this time we are going to focus on these 4 values, excluding this one here, the velocity, final velocity, and this then leads us to use s equals ut plus a half at squared. So what can I enter into this? 0 equals u sine theta multiplied by t minus a half gt squared. And it's a quadratic equation. I'm going to factorise this quadratic by taking out a t, which leaves me with u sine theta minus a half gt. Now from here, if we self-solve this quadratic equation, we'll know that we get t equals 0, which is the start of the journey. And then the other alternative is that u sine theta minus a half gt equals 0. And what we're going to do is rearrange this result so it gives us a result for t. So t is equal to 2u sine theta all over g. And we now have established a formula for the time of flight, a general result for the time of flight. Now, I can also take that result that we've just found and I can substitute it into this result here, which we found looking at the horizontal motion. So the horizontal motion analysis tells us that r is equal to u cos theta multiplied by t. So I can now replace t with 2u sine theta over g, which gives me a result for r, which is 2u squared sine theta cos theta over g. Now I can do a bit of further simplification on that because we have 2 sine theta cos theta here, and I can replace that by sine 2 theta using a trigonometric identity, which gives me r equals u squared sine 2 theta over g. And we have a third general result because, of course, r is the horizontal range. So in just a short space of work, we've established a general result for the maximum height, a general result for the time of flight, and a general result for the horizontal range for any projectile. Remember how general this projectile was. We didn't have a specific velocity of projection, we didn't have an angle of projection other than calling it theta, so all of this is highly generalised. So we're now going to investigate the maximum possible range. Here's the formula again, r equals u squared sine 2 theta over g. Now g is fixed and equals 9.8 metres per second squared on Earth, so we can ignore that for the moment. With u, increasing u will increase the range and vice versa. But the real focus is, how does the angle theta impact range? To think about this, we need to think in more detail about sine 2 theta. Now, you should know that the maximum possible value of any sine function, and sine 2 theta, is equal to 1. We know that the sine curve doesn't go up above 1 as an upper limit. Now, if sine 2 theta equals 1, that means that 2 theta must equal 90 degrees, which means theta equals 45 degrees. And this is the angle you choose, completely independent of velocity, if you want to maximise range. Now, the last thing that we're going to do is to find a general Cartesian equation for the trajectory. So here's a sketch diagram with all of the information marked on that we have seen previously. Here's my general point P with coordinates x and y. I'm going to find x and y in terms of t and use that to then eliminate the parameter t and find a Cartesian equation connecting x and y. Remember, x and y are the general coordinates of a general point P, so they represent its horizontal and vertical distance travelled. Let's analyse the motion from O to P. We've done this for many, many specific examples with numerical values of speed and the angle. Let's now do this for a general situation. Speed equals distance over time, so our horizontal speed, u cos theta, equals the distance travelled x over the time taken. So x is equal to u cos theta multiplied by t. There's one of our parametric equations. Now, our vertical motion, suvat, s equals y, u equals u sine theta, v equals the velocity at p, the vertical velocity at p, a equals negative g, and t equals t. So ruling out v, and then making use of s equals ut plus a half at squared, we get y equals u sine theta t minus a half gt squared, equation 2. So let's go back to equation 1 first of all, and let's rearrange this. So t is equal to x over u cos theta, and substitute this into equation 2. So this then tells me that y equals u sine theta, and in place of t here and here, we're of course going to substitute in x over u cos theta. Like so. Now, all that's left is to try and simplify this. So this gives me y equals, my u's here will cancel, and I'm left with x sine theta over cos theta, and you should be thinking about what you could do with that in a minute. And over here I've got gx squared over 2 u squared cos squared theta. Now the last small bit of simplification that I'm going to do is to remind myself that sine theta over cos theta is the same as tan theta. So I can rewrite this as y equals x tan theta. And then this part over here, 1 over cos squared theta, is of course the same as sec squared theta. So I'm going to rewrite this as gx squared sec squared theta over 2u squared over here. And we're done. We've now found a general equation for the trajectory of the projectile in terms of x and y, and of course for any specific situation values of theta and u can be substituted in. Don't memorise these equations, but think about the process from which we derived them, because that's the important part. You're not expected to memorise each and every one of these equations, but you are expected to understand and to be able to recreate the techniques that brought us to these generalised equations.